Hi everyone, this is Miss Moore and today we are continuing with Lesson 2, Solar Energy Interactions. The focus of today's lesson will be how solar energy interacts with the different spheres, atmosphere, hydrosphere, and geosphere. If you don't have a copy of the lesson notes in front of you today, please feel free to make your own notes on lined paper or by typing them out in a document. We're warming up with the following question today. People use greenhouses to grow plants during the winter or plant seeds in the spring so they can germinate and be planted outside when the weather gets warmer. A greenhouse is a building whose walls and ceiling are made of glass or clear plastic composites. A greenhouse stays warm on the inside even when it's cold on the outside. Sketch lines representing solar rays on the diagram of the greenhouse below to show how you think this occurs. Please pause the video here while you think about this. Okay, let's think about this together. When solar radiation encounters the walls of the greenhouse, there's a couple different things that happen. Some of those rays are going to be reflected off and not contribute to the heating of the interior. Other rays are going to pass into the greenhouse and possibly then reflect out, giving some of their energy to the interior. Still other rays may enter and bounce around inside, reflecting off the walls of the greenhouse. These are the rays that give the greenhouse the most heat energy over time. What happens inside a greenhouse is basically what happens in our atmosphere, hence why we've called it the greenhouse effect. If we had to summarize it, we would say that it is the process of trapping the sun's heat energy between Earth's surface and the atmosphere, as solar rays are reflected and absorbed. When sunlight enters Earth's atmosphere, it takes one of three paths, much like it did in the greenhouse. It can be reflected by the atmosphere, and in fact, it's the clouds or the water vapor in the atmosphere that do most of the reflecting. The rays can also be reflected by the Earth's surface. Specifically, ice sheets reflect the most sunlight, or the rays can be absorbed. And the parts of Earth's surface that do the most absorbing are the land and the oceans. Now, you wouldn't think that oceans do a lot of absorbing, but they do. And it's due to their dark color and their heavy content of matter. So, seawater is not just pure water, it's got loads of additives, loads of organisms, and other forms of organic matter which absorb all of that energy. Next, we're going to watch a short video on YouTube called What is the Greenhouse Effect? You can access this video by clicking on the link in the lesson notes or searching for the video by title when you get to YouTube. As we watch, we're looking to answer the following questions. How cold would Earth's surface be without the greenhouse effect? And what happens when the concentration of carbon dioxide, methane, and nitrous oxide in the atmosphere increases? Please pause the video here while you go to YouTube and watch this short film. As you saw in the video, the average surface temperature would be negative 18 degrees Celsius without the greenhouse effect. It's a very important phenomenon that makes the surface of our planet habitable for us. So the greenhouse effect is a good thing. It's often talked about in the media as a bad thing, but we need to keep in mind it's a natural warming cycle which benefits all of the organisms that live on Earth's surface. You just can't exacerbate it too much. So when you get too much carbon dioxide, methane, and nitrous oxide in the atmosphere, there's all of these extra particles which reflect the solar radiation. The energy becomes trapped between Earth's surface and the atmosphere, and the surface begins to heat up. Let's draw a diagram that summarizes the exact parts of the interaction between the solar energy and Earth's surface. So I'm going to draw a little dashed line here to represent the upper layers of the atmosphere. And here's the sun. So case one is that the solar radiation is reflected off the atmosphere. Case two is that there's no reflection and the radiation makes it through to Earth's surface where it's absorbed. Case 3 is the solar radiation is incident on reflective components of Earth's surface, such as ice. Now, some of that radiation will escape again as it reflects off the ice, but much of it will start to undergo a repeated cycle of reflection between different layers of the atmosphere and Earth's surface. So this is case 4, and we're going to call this repeated reflection. There's another phenomenon that they mentioned in the video we should also be aware of, and that's when the Earth's surface is warm, it will actually radiate energy back out into the atmosphere. So I'm just going to call this natural radiation to atmosphere. And we're just going to make a little side note here that the repeated reflection that's occurring in step 4 is as a result of the greenhouse gases in the atmosphere, which absorb and re-emit the energy in many directions. So let's talk a little bit more about these greenhouse gases. Technically, any gas in the atmosphere that is part of this cycle where it absorbs and reflects solar energy is a greenhouse gas. Common greenhouse gases that are being produced in excess by human activities include carbon dioxide, or CO2, methane, or CH4, and nitrous oxide, or N2O. Surprisingly, water vapor is also considered a greenhouse gas, or maybe not so surprisingly, because we know that they are not evil, they're useful, and they're meant to be there, and water is very good at absorbing and reflecting solar radiation. So just a quick note here, remember greenhouse gases are a good thing. The warming effect that they provide keeps the Earth's surface warm enough to live on. Thank you, greenhouse gases. However, the current concentrations of these gases in our atmosphere are too high to be sustainable, and this is the primary cause of climate change. So now we've mentioned a couple greenhouse gases by name, specifically carbon dioxide, methane, nitrous oxide, and water vapor. I would like you to brainstorm what you think are the primary sources from which these gases arise. What are the primary sources of emission? And after you've made all of your guesses under the I think column of example 1, then conduct some quick research online to verify your guesses. What does your research say are the primary sources of emissions? When you're finished with your research, please reflect below on which of the primary sources above surprised you the most. What did you not expect? Please pause the video here while you do this example. The primary source of carbon dioxide is burning fossil fuels, such as burning gasoline in cars, burning jet fuel in airplanes, and so on. Methane primarily comes from microbial processes. That's when anaerobic bacteria are breaking down nutrients. They release methane as a byproduct of that process. And where you find that happening is in the gut of cows. And so cows are producing a lot of the methane that we're dealing with in our environment right now. Nitrous oxide primarily comes from agricultural activities and water vapor as a result of the water cycle. Sunlight hits our Earth unevenly because the Earth is tilted 23.5 degrees off its plane of orbit. This is called axial tilt. And so as a result, the sun hits the Earth at different angles. We know that solar energy provides us with heat or thermal energy. And the amount of solar radiation produced by the sun is constant, but the amount that reaches us on Earth varies. Because of the fact that our planet is spherical and tilted at 23.5 degrees, the energy strikes the curved surface at different angles. Earth receives much more direct solar energy at lower latitudes, like in Mexico. As a result, the atmosphere heats up unevenly. In region A on the diagram, we have sunlight scattered over a large area with less intensity, so this is called diffuse warming. Region B lies closer to the equator, and so we get more concentrated warming. And region C is lined up perfectly with the equator, where we get highly concentrated warming. This uneven heating of Earth's surface is what produces winds. Warm air near the surface rises and then cools. While it cools, it densifies, because cold air is more dense than warm air, and this air sinks, creating wind that moves warm and cool air around Earth in cycles. Therefore, wind results from the unequal heating of Earth's surface. And because of the movement of this air as a result of these natural cycles, in the end, heat gets distributed to places that it usually wouldn't reach as easily. Wind plays an important role in redistributing all the thermal energy from the sun around the Earth. Next, we're going to watch a short video on wind with Bill Nye the Science Guy. As you're watching, draw a simple diagram to show how wind is generated, using the same model that Bill Nye uses in the video. Please pause the lesson video here while you visit YouTube and search for this video by title or by clicking on the link in the lesson notes. Using the same model that Bill Nye used in the video, we can represent the land, the ocean, and the northern and southern poles of the Earth, which are covered in ice. When the solar radiation comes down and warms the land and ocean, it warms the air above the land and ocean as well. And that warm air becomes less dense and it rises. As it approaches the cooler areas of the Earth, it densifies and begins to sink, and you end up with a constant cycling of warm and cold air, which rises and falls based on its density. This is how wind is generated. Because Earth is heated unevenly, the oceans are also heated unevenly, with the oceans closest to the equator absorbing the most thermal energy, and the oceans farthest away from the equator absorbing the least thermal energy. So, how is this energy distributed throughout the oceans? That's a result of ocean currents. Surface currents are created by wind, and you can see that in this diagram. Some of the most important surface ocean currents are represented here, and some of them are so important in terms of defining the subclimate of different regions that we've even named them as we monitor them. In all ocean basins, the warm water currents near the equator flow in a westerly direction. When these currents encounter a land mass, they turn toward the poles. You can see this in the diagram. For example, the south equatorial current, which carries warm water, turns into the East Australian current as it moves south past Australia and curves towards the South Pole. In fact, this is the current mentioned in the Disney film Finding Nemo. The poleward flowing currents carry warm tropical water into higher, colder latitudes. As the waters cool, they begin flowing towards the equator again, bringing cold water to tropical regions. As the Earth is heated unevenly, the oceans are heated unevenly as well, resulting in a difference in temperature, which drives deeper water ocean currents. The other factor in these deep ocean currents is salt content or salinity. We know that colder things are denser, and this is true for water as well. Cold water is denser, it sinks below the warmer water, and saltier water is also denser. So this water sinks and displaces more of the diluted water around it. Together, these produce a massive system of deep water currents called the Great Ocean Conveyor Belt, or thermohaline circulation. This belt of moving water carries heat and nutrients around the world. Next, we're going to watch a short video called Bill Nye the Science Guy on Ocean Currents, available on YouTube at this link, which you can click on in the lesson notes or search for the video by title. As you're watching, draw a simple diagram to show how ocean currents are generated. Now, Bill Nye is going to show you the effect of salinity, but I would also like you to consider varying temperature across the globe as you construct your diagram. Please pause the video here while you visit YouTube. Bill Nye's model was quite simple and demonstrated that saltier water is denser and sinks. Let's make our model a little more sophisticated to account for ocean temperature as well. Near the equator, there's lots of solar radiation that heats up the water. Warm water is less dense, and so it rises. Interestingly enough, there's actually quite a bit of rain at the equator. The tropics receive the most rain on a consistent basis. As a result, the fresh water falling into the ocean helps decrease the salinity of the surface water in that region. As the salinity decreases, the water rises even more. But then as it circulates up towards the poles, the temperature is starting to cool and the water is becoming denser and sinking. This is happening simultaneously with lots of melt from the ice at the poles, which decreases surface salinity, yet the temperature is so low at that point that densification is inevitable. This cycle continues, driving the deep ocean water currents known as thermohaline circulation. Okay, everyone, that's it for today. It's time for your assignment on ocean circulation. Bye for now.